I am Amrita from Institute of Aeronautical Engineering, Department of Electronics and Communication Engineering. My tech talk topic for VLSI design is threshold voltage variation control. Introduction to threshold voltage variation. Understanding the importance of threshold voltage in semiconductor devices. Variations in threshold voltage can significantly impact device performance and reliability. This presentation explores methods to control and minimize with variability. Causes of threshold voltage variations. Process induced variations such as doping fluctuations and oxide thickness changes. Short channel effects and device scaling contribute to threshold voltage shifts. Here, threshold voltage is denoted as VTH. Environmental factors like temperature and supply voltage also impact VTH. Impact of threshold voltage variation. Increased variability leads to unreliable circuit performance. It can cause timing issues and reduce yield. Managing VTH variation is essential for robust VLSI design. Techniques for threshold voltage control. Process optimization to reduce doping and oxide thickness variability. Device engineering approaches such as channel engineering. Use of threshold voltage adjustment in plants. These are some of the techniques for the threshold voltage control. Process control strategies. Tight control of doping concentration during only the fabrication. Uniform oxide growth and deposition techniques. Advanced lithography for precise device patterning. Material engineering approaches. Incorporation of high K dielectrics to stabilize threshold voltage VTH. Use of alternative channel materials like silicon, germanium. Surface passivation to reduce interface traps affecting VTH. Device design techniques. Adjusting device dimensions to mitigate VTH variability. Implementing multi-gate or FinFET structures for better control. Engineering source or drain regions to influence threshold voltage. Threshold voltage adjustment implants. Use of doplant implants to set VTH post fabrication. Tailoring implant doses to compensate for process variations. Ensuring stability of adjusted VTH over device lifetime. Use of work function engineering. Selecting gate materials with appropriate work functions. Modifying the gate work function to tune VTH. Employing the metal gates for precise work function control. Statistical and modeling approaches. Employing statistical process control to monitor variations. Using compact models to predict VTH fluctuations. Implementing design for variability techniques. Circuit level compensation techniques. Incorporating adaptive biasing to stabilize VTH effects. And using redundancy and error correction to improve reliability. Designing circuits tolerant to device parameter variations. These are the techniques for circuit level compensation. Advanced fabrication techniques. Atomic layer deposition for uniform dielectric layers. Self aligned process to reduce the variability. Integration of new materials for better VTH control. Reliability considerations. Ensuring VTH stability over time and under stress conditions. Mitigating hot carrier effects that cause VTH shifts. Conducting accelerated testing to predict long term behavior. Emerging trends in VTH control. Adoption of machine learning for process optimization. Development of new device architectures for better control. Integration of 2D materials for reduced variability. Challenges in VTH variation control. Scaling down devices increases susceptibility to variability. Balancing the process complexity with manufacturing costs. Ensuring compatibility with existing fabrication infrastructure. Coming to the case study, FinFET technology, where FET is field effect transistors. So, FinFETs provide superior gate control, reducing VTH variability. Challenges include controlling multiple interfaces and dimensions. Process innovations have improved VTH stability in FinFETs. So here we can see the FinFET internal structure of the FinFET. Here up we can see the nitride spacer, gate electrode, replacement gate metallization, and here the source and drain are in the orange color, and coming to the light blue color is the shallow trench isolation, and here we can see the last one, the high K dielectric in between the source and drain. Coming to the future directions, continued research into novel materials and device structures. Integration of real-time monitoring for process adjustments. Developing standardized matrices for the VTH variation assessment. Coming to the summary and the conclusions. Controlling the scaling down devices increases the susceptibility to variability. Balancing process complexity with manufacturing costs. Ensuring compatibility with existing fabrication infrastructure. So FinFETs provide this superior gate control by reducing the VTH variability, and this process innovations are improved by the threshold voltage stability in the FinFETs. So here we can see the continued research into novel materials and device structures. So for integration of real-time monitoring in the future directions, we can see the adjustments of the threshold voltage. Developing standardized matrices for VTH variation assessment. So coming to summary and conclusions, controlling VTH variation is vital for high performance reliable devices. A combination of process, material, device and circuit techniques is employed. So these are the techniques which are employed for the threshold voltage variation. So, ongoing innovation is essential to meet the demands of future semiconductor technologies. Thank you.